Good day. My name is Shaniel Davrajh. I'm an engineer at the Center for Robotics and Future Production at the CSIR. My presentation today is titled Learning Factory, Growing into Digital Transformation for the Fourth Industrial Revolution. It's based on a facility we're developing where we're looking at innovative technologies to address the skills gap for digital transformation. I'll begin with the modern trends that we face in our society. The first is that with the fact that we live high-paced lifestyles. This places a strain on performing everyday tasks. We have to balance work, managing our households, and our health. A recent study at the University of Oxford showed that South African employees work amongst the longest hours in the world. Furthermore, a South African study showed that last year alone, we spent a significant amount of time in traffic. The time lost to congestion in Johannesburg for an individual on average was estimated at 74 hours. In Pretoria, it's estimated at 65 hours. And in Cape Town, a whopping 124 hours was lost due to people spending time in traffic. The second trend that we notice is that globalization of markets makes more products available and accessible to everyone, even in remote locations. The third trend is that we want to be socially relevant and that we want to be able to communicate on the same platforms as our counterparts in first world countries. We want the same technologies, possibly the same lifestyle that we see popularized in media. Put simply, we more often than not want something because somebody else has it. This is known as the Diderot effect. This means that we need things faster. We need more accessibility to technology. We want more convenience. And we also want more personalized technology. The impact on technology requirements based on these modern trends include the fact that we need more insight into systems and products to be more efficient. We need modular designs to accommodate more customization. We need flexible and agile systems to respond to changes in global markets. We need integrated systems to function collaboratively and instead of in silos. We need standardized operations to ensure that we're delivering the correct quality. We need to look at smart systems or enabling the development of smart systems. We need smart systems wherein we have high levels of automation and self-optimization. We have to have more focus on ergonomics. And lastly, we need to facilitate customization on a mass scale or mass customization. The way in which we can do this is to continually improve the technologies, processes, and people we have of today. One enabling technology is referred to as digital transformation. Digital transformation is the integration of digital technology into all areas of a business, fundamentally changing how it operates and delivers value to customers. It marks a radical rethinking of how an organization uses technology, people, and processes to fundamentally change business performance. The key aspect of digital transformation lies in the way in which we process, communicate, and store information. I'm going to touch on an example of digital transformation that we see in everyday life, and that's to do with cooking. Here's an example of an older model coal stove that was traditionally using coal or wood to provide heat to do the cooking. Fast forward, we would use electricity and we would have analog controls. And this would give us much more control over the heat and the way in which we transfer the heat to the pot. If we fast forward to modern day technology, we have digitally controlled stoves, which can function in certain routines. That is, you can have a high heat for a certain time and a moderate heat for another time. And this can be done digitally. The ultimate goal is the same in that we're cooking food, but the way in which we do it and the technology we use to do it has changed. On the bottom, you see a smart cooker, which has predefined routines to cook different types of meat. This is to ensure consistency of the meal every single time, to such an extent where even I can provide a meal. But all of this has an application of a higher level. The example you see here is dealing with home automation. On the screen, you can see an example in which a tablet is used to control the security, the air conditioning, televisions, and washing machine within a house. Again, the same functions are being performed as before, the way in which we control it and the insight in which we have to the system has changed. The impact of digital transformation lies in the fact that technology is a massive value creation lever for companies. There's an exponential evolution of technology that has been observed, and there's 3 laws surrounding this. Again, dealing with the processing, communication, and storage of information. Moore's law deals with processing power doubling every 18 months. We've seen this over the past few decades. Butter's law states that communication doubles every 9 months. And if you look at the 5G connections that we have nowadays, you can see an example of that. Kreider's law looks at the storage capacity doubling every 13 months, an example of which would be the capacity of your phones. The implication of this exponential growth is that there's a gap created if technology develops exponentially and businesses develop linearly. Think of examples like Kodak, Blockbuster, and Nokia. The impact on traditional business architectures of whole industries has to also be noted. The evolution of links between different economic agents across the value chain is prevalent, and there's also an impact on individual companies in terms of their ability to earn revenue and profitability. Digital transformation is seen as the focal point of the 4th Industrial Revolution. You've seen this diagram before, where we have an evolution of technologies from steam power to cyber-physical systems. But what not many people know is that the 1st Industrial Revolution, which looked at harnessing heat in the form of steam, had a lag in terms of its accessibility to technology. The first steam locomotive was built in 1802. However, the first steam locomotive was received in South Africa in 1859. Almost 60 years later. The difference between the 1st Industrial Revolution and the 4th Industrial Revolution is the democratization and accessibility of the technologies. And now let's have a look at the 4th Industrial Revolution. Moving on to the global skill trends that have been identified by the World Economic Forum, we find that a lot of the technologies associated with the 4th Industrial Revolution are key in the future of any society. In terms of digital benchmarking, a recent study published in the Harvard Business Review showed that South Africa is much more suited to adopting digital transformation than any of its counterparts in Africa. But there are some challenges. The adoption of technology in South Africa is relatively low compared to other countries in the world. There are concerns with regards to unemployment. Over 50% of youth are unemployed. That's ranging from 15 to 34 years. Over 2 million people have lost all income under the lockdown. The inequality levels are the highest amongst the world. The top 10% take 65% of the country's income. There's concerns around literacy levels, and there's a trend that companies want candidates with sound competencies more than just qualifications. And what this means is that candidates now seeking a job need experience, but they need a job to get that experience. And therein lies a challenge. The rate of technological updates often surpasses the skills development, and there's a big skills gap in the country. And whilst technology is readily available, it's not easily accessible to small and medium enterprises, cost being the biggest factor for this. So let's look at a quick summary of what we've discussed thus far. Technology advances rapidly and is much more accessible now than ever before. A study in 2018 showed that 95% of the adult population in South Africa uses a mobile phone, and of that, 60% being a smartphone or being smartphone users. South Africa is benchmarked as having the highest potential for adopting digital transformation in Africa. Adoption of technology in South Africa is relatively low compared on a global level. South Africa is ranked 14 out of 16 G20 countries on the Accenture Platform Readiness Index. So we have the potential to adopt technology, and there are technologies that are readily available. But we still have a very high unemployment rate, especially in the youth. The World Economic Forum attributes this key challenge to the lack of enough and appropriate skills. Our response to these challenges is that we've embarked on a project with the Mesita to develop a platform that uses innovation to bridge the skills gap for the fourth industrial revolution. This platform is referred to as the Learning Factory. A learning factory is an idealized replica of a work environment. The concept of a learning factory began in the 1990s, wherein the automotive industry wanted to fast-track the integration of students into the working environment. Fast forward to 2016, a work group was created which focused on education for the fourth industrial revolution. This group identified learning factories as a key enabler to skills development for 4IR. A learning factory is better suited to skills development and innovation than a real-world working environment because it's not exposed to complex and volatile value chains. Real-world working environments experience challenges when it comes to skills development and innovation. The reason for this is that they are part of bigger value chains and they are product and bottom line oriented. These constraints or these challenges aren't present in a learning factory, which makes them suitably poised for skills development and innovation. The value proposition of the learning factory is that we will bridge the gap between industry and skills development, industry and research development and innovation, and skills development and research development and innovation. In doing so, we can produce employable learners, and we can strengthen the connection between the CSIR and industry, as well as upskill CSIR staff in the space of 4IR. So now we come to the overview of the Learning Factory. Our definition is that a learning factory is a technology platform which will support the skills development and innovation as well as best practices in the context of 4IR systems. The objectives of this learning factory are that it will serve as a skills development platform. It will also serve as a reference for learning factories that will be installed throughout the country. And lastly, it will serve as a platform for innovation with respect to applied research enabled by 4IR technologies. And examples that you see here are de-risking of technologies, product development, techno-economic studies, as well as product localization. The objectives of the Learning Factory will then contribute to the National Skills Development Plan, which focuses on skills development in South Africa. It will also contribute to the CSIR strategic objectives. Here we see the Learning Factory structure. At the core of it is digital transformation, which focuses on continuous improvement. This is enabled by 4IR technologies, which are considered disruptive technologies or enablers, and I'll discuss that more in detail as we go along. The first environment that you'll encounter in the Learning Factory is the Learning Lab. which will focus purely on skills development. We also have research labs, which will focus on innovation, and experience centers, which will cultivate experiential learning and innovation. And as we move from the learning lab to the experience centers, the input from the learner is going to increase. The process that we're going to follow for digital transformation is seen here, which is adapted from Deloitte. It's done in 3 phases, and the first phase being physical to digital. The second phase is where we work in the digital space, and the third phase is where we move from digital to physical. And what happens here is that when we move from physical to digital, referred to as digitalization, we get digital signals from a physical piece of equipment. Once we have those signals from the physical equipment, we then create what is referred to as a digital twin of that piece of equipment. That digital twin is basically a mathematical model which we use to gain insight and understanding into the operation of that piece of equipment or system. Once we have sufficient understanding of that system, we can then make modifications to adapt it to changes that are needed. This is the third phase, which is often referred to as virtual commissioning. An example of this process is seen on the screen. On the top right, you see a mechanical lathe. If we instrument it and get information on specific parameters, we can create a digital twin of that lathe. If we get sufficient understanding of that model, we can then use the information to understand its current state, as well as predict its future state. That adds value in how we use the machine in our business. The overarching application of all the information, or the digital transformation, lies in the applications of tool tracking and tracing, energy monitoring, intelligent worker assistance systems, paperless quality assurance, digital shop floor management, and condition monitoring. The envisaged evolution of the learning factory begins with a single machine working within a process, that process functioning within a system, and that system being part of a bigger system of systems. An example we have here is a robot, which functions as part of a process or a work cell, that work cell being part of a workshop, and that workshop being part of a system of workshops. In moving from a single machine to a system of systems, you need to have an understanding of the skills, technologies, and best practices associated. That's fundamentally what we're going to house in the learning factory. In doing so, we will provide a platform for skills development, manufacturing support, and localization of technologies. Speaking of technologies, the 4th Industrial Revolution is based on a number of technologies, and we've highlighted 10 of the most suitable technologies to house in the learning factory. That being artificial intelligence, cybersecurity, the industrial Internet of Things, big data, cloud and edge computing, robotics, additive manufacturing, system integration, simulation, and augmented reality. The links to the different clusters in the CSIR are quite evident. For example, technologies for the 4th Industrial Revolution can easily be applied to the agricultural sector. For example, the results of the in-situ testing of soil being sent to a fertilizer producer such that the farmer gets the fertilizer that's needed for his farm before he even realizes it. The application of the learning factory also has wide reach in the healthcare system, smart mobility, smart places, defense sector, manufacturing, as well as mining. Let's begin quickly with the first technology, that being artificial intelligence. This is a branch of computer science dealing with the simulation of intelligent behavior in computers. The application of artificial intelligence spans healthcare, robotics, marketing, business analytics, manufacturing, chatbots, etc. The list is non-exhaustive. Fundamentally, artificial intelligence is the driver, or is the key driver behind the 4th Industrial Revolution. In terms of the learning factory applications, we will be using artificial intelligence for quality checks, predictive maintenance, scheduling, training, waste management, model-based decision support, a WhatsApp-based health diagnosis system, to name a few. The next technology is robotics. And basically, robotics is a field which involves the design, construction, and use of machines, referred to as robots, to perform tasks done traditionally by human beings. More often than not nowadays, however, we are finding that robots are able to do jobs that humans are not able to, such as working in hazardous environments. The general application of this technology spans manufacturing, healthcare, agriculture, mining, logistics, and the military. In terms of the learning factory applications, we will be applying robotics to assembly processes, materials handling, agriculture, human-centered automation in which we look at collaborative and intelligent robots, mining, rail inspection, and even drone applications. I'm going to show you a video now of one of the robots that we've built that have been applied to the agriculture sector.
The CSIR, in partnership with Stellenbosch University, has developed this technology called DASI, which is a mobile platform that drives through a vineyard and takes measurements. South Africa is one of the top wine producers in the world, and it's very important for our industry to remain competitive. It generates a lot of income for South Africa, a lot of foreign currency coming into the country because of the wines we produce. The technology that we've introduced helps a farmer to understand better what's going on in his vineyard. The same technology can be used in citrus environment or other horticultural environments. The challenges that a farmer has are understanding how the soil actually supports his plant. So he needs to understand what additives he needs to put into the soil to ensure proper growth of his plants. He needs to also understand moisture levels and how that affects his growth. And then he needs to understand solar irradiation, all kinds of different parameters, and all of those things together helps him to understand how the plant is growing. CSIR implemented a mobile system that allows transport of sensors throughout a vineyard. It'll measure on a point-by-point basis and fairly high resolution what's happening to each plant. We provide for each plant actual geolocation tagging, so you understand which plant you're busy measuring. And then if you keep on doing this on enough intervals, you get historical data and you get a growing trend for your plant, each and every plant. The DASI platform is basically electrically operated robot. It's fully autonomous, so you can tell it which path it needs to follow. It'll do obstacle avoidance using some onboard sensors. So it does its own battery management, traction, all that sort of stuff is built in. On that level, once it's an autonomous robot, we pass it on to our colleagues or partners at Stellenbosch University, who then outfit it with specific sensors that they deem they need for a specific run. So in certain cases, they will use laser scanners to look at the canopy and growth of the plant. In certain cases, they will put ground sensors to actually check the soil content. And in certain cases, they will use hyperspectral sensors that looks at the actual grape. So that, in theory, should give you sugar content. That's just something that we haven't proven yet, and that's what we're busy developing right now.
The DASI uses its big wheels and big motors to silently carry these sensors through the corridors of the vineyard. The sensor array that is mounted on top of the DASI consists of visual, near-infrared and infrared sensors that monitors the grapes and the plant's growth. Currently we are testing a prototype in the vineyards of the Stellenbosch region to evaluate the sensor data and bringing the scientific data and the farmer's needs together.
What's important to us is localization. We could have imported a robotic platform. There are one or two available from overseas, although none of them seem to be especially suited for our environment. So we made the decision of developing our own. And it's important to us to have that local content, the local ability to support the instrument, because what we've seen again and again, you import something, it gets used, it breaks down, and then suddenly there's no support. Either you have to import really expensive spare parts, or you have to fly in an overseas expert, which costs a lot of money. So this localization is an important thing for us, and that's when we made the decision of developing it ourselves. And then on the sensor side, there's a huge need for development of local sensors, which are lower cost than what is currently being imported. For instance, the sensor that's being used for the hyperspectral imaging, we're busy with a local company and seeing if we can't do a local development together with them versus importing millions rand of sensors. It's really an expensive item to import. So we're trying to play a role there as well, lower cost sensors, making the whole solutions more affordable. Having DASI around basically assists the farmer to have a much better feel what's happening in his vineyard. Currently it's much a gut feel of what's going on with the plants. With DASI, you'll get some real data that you can use to make actual decisions on managing your vineyard.
The next technology that we'll house in the Learning Factory is the Industrial Internet of Things. This refers to the application of the Internet of Things technology in industrial settings, especially with respect to instrumentation and control of sensors and devices that engage cloud technologies. The application in general of Industrial Internet of Things spans smart manufacturing, predictive and preventative maintenance, smart power grids, smart cities, connected and smart logistics, and smart mining. With respect to the Learning Factory application, we will be using the Industrial Internet of Things for digitization, equipment integration, a low-cost hardware development, as well as monitoring of water quality. The next technology is additive manufacturing, more commonly known as 3D printing. The general application of this technology spans the aerospace, defense, tooling, automotive, medical, transportation, rapid prototyping, and reverse engineering industries. In the Learning Factory, we will use additive manufacturing to produce customized components, and the facilities that we have available are desktop printers, as well as the facility available from the Technology for Special Operations and the Aeroswift 3D printer. Here you see an example of additive manufacturing. The housings for these face shields were produced at our Technology for Special Operations unit for the South African National Defence Force. The next technology we will house is cybersecurity, and basically this is the science that involves technologies which keep us safe from cyber attacks. The applications to the Learning Factory include blockchain applied to facial recognition, biometrics, and ensuring that our design content is safe. Simulation is the process of mathematically modeling a real-world system. The applications within the Learning Factory include digital twinning, design, virtual commissioning, and plant simulation. The Learning Factory has access to a multitude of 3D CAD software that's for design and analysis, plant simulation, operational management software, digital twinning software, and the focus will be on design, optimization, and virtual commissioning. Big data is simply a field focused on how we handle large, more complex data sets, especially from new data sources. We will be using big data in our Learning Factory in conjunction with artificial intelligence to gain insight and understanding of the systems we address. Cloud and edge computing involve resources that are available on the internet to perform computing tasks that we would ordinarily have to do on our desktop. The access to high computational power makes it very lucrative to handle the big data sets that are generated when we instrument our equipment. The Learning Factory applications for cloud and edge computing include databases for predictive maintenance, student tracking, production planning, as well as real-time information communication and processing. System integration involves the software tools that enable vertical and horizontal system integration. These applications include manufacturing and industrial value chains. At the Learning Factory, we will be housing PLM training software, which includes Team Center and Op Center from Siemens. And I'll now show a video on the application of system integration.
Many of today's leading businesses understand that developing new products is increasingly complex. They recognize the need to leverage digital technology to innovate, collaborate, and launch new products. At Deloitte, we've built a practice to help our clients transform their product development capabilities by leveraging digital technologies to increase the efficiency and effectiveness in how they design, develop, integrate, make, and support new products. For example, Deloitte helped a global aerospace and defense manufacturer who had grown through dozens of acquisitions in the past 10 years, each business operating independently with completely different product development processes and tools. Charged with improving global collaboration and engineering efficiency and effectiveness through use of digital technologies meant standardizing to one common process that would provide the rigor and flexibility needed by each market and product the company serves. Deloitte's predefined product development processes and pre-configured Siemens PLM solution helped the company to rapidly standardize on a global process and single PLM system with flexibility for each market and product type. Leveraging a single digital thread across their engineering architecture to help them develop the next generation of integrated products, Deloitte helped the organization define their strategy, roadmap, and approach to rapidly achieve the impossible. With over 350 million data objects migrated, possibly the largest in the industry, and at a 99.5% accuracy rate, they standardized on a common data model, fully integrated mechanical design, electrical design, and software and interfaces to SAP, and rolled out 22 training courses to over 10,000 of their global workforce with tools such as robotic process automation, augmented and virtual reality, and advanced analytics for improved prediction and accelerated decision-making. Process redesign was approved in month 6, with pilots launched by month 9, and successive deployments in months 14 through 17. Building on phase 1 of their transformation, the company is exploring advanced digital capabilities to further enhance and improve engineering efficiency and effectiveness. Deloitte is helping enterprises innovate differently and bring their business visions to life. What is your digital vision?
The last technology that we'll be housing in the Learning Factory is augmented reality. And this is a technology that superimposes computer-generated images onto a user's view of the real world, providing a composite view. The applications of augmented reality within the Learning Factory include augmented reality for training, to assist with lectures, performing quality checks in the assembly cell, use as a visual tool, and maintenance and operation of certain systems. Here you see how augmented reality can enhance the learning experience for learners reading from their notes. I'll now show you a video on augmented reality in practice.
The city of Toul has one of the most modern combined cycle power plants in France. Celeste has not only commissioned Siemens to build this plant, but also to operate it under an operation and maintenance contract.
There's a will in any plant operated by Siemens Service to provide the best efficiency. So we are operating the plant of Toul as if it were our own.
What if we have a completely digital chain from collecting data, evaluating data, and have post-processing of data? My opinion is that augmented reality can help to achieve this. That's my vision.
Siemens uses professional-grade augmented reality as a versatile tool for the digitalization of power plant services, during operation as well as for staff training.
The DACRI helmet, I think, is going to be a great component for our training for the Operating and Maintenance Centre. It's going to expand our portfolio and be able to train on-site. So you've got operators training locally via the augmented training.
It's a very amazing experience, and well, actually it's very simple to use.
Welcome to the Siemens Operating and Maintenance Training Program. You're ready to start your first training session.
Trainees can familiarize themselves with the processes in the power plant step by step by using virtual work instructions, prepared training sequences, or remote assistance directly from a trainer.
Well done. You passed the first part of your training.
Well, it was like a new world full of technology and innovation, a new way of life.
The DACRI Smart Helmet can also be used as an intelligent solution in operation and maintenance. A big advantage? The communication with the Siemens SPPA T3000 control system is possible, therefore allowing digital measurement and operating data to be immediately available wherever they are needed.
Avec le casque DACRI, l'avantage c'est qu'on pourra travailler les mains libres et je pense que c'est vraiment le futur de l'industrie de travailler avec ce type de casque.
The operation engineers use the helmet as an on-site information tool and can communicate directly with colleagues in the control room via remote expert.
Pierre, pour la salle de contrôle.
Oui Pierre, je t'écoute.
Alors j'attends instruction, je suis au sampling conteneur.
Tu peux ligner pour la partie HP.
Bien reçu, je commence les réglages.
Je te remercie.
C'est très pratique d'avoir la fonctionnalité thermique directement intégrée au casque. Ça, pareil, ça évite d'avoir à retourner à l'atelier pour aller chercher le matériel, pour aller faire ce relevé thermique.
Digitalization is not the future, it's the present.
Siemens is driving digitalization on all levels, and augmented reality is one piece in this game, definitely.
Moving on with the structure of the Learning Factory, we'll now look at the Learning Lab, which is the first component of the Learning Factory. This platform, again, is focused on skills development and comprises of three components, that being theoretical training stations, practical training stations, and application cells. The concept of a Learning Factory is to learn by doing, and hence the theoretical training content will be kept to a minimum. The practical training stations will be designed in a modular fashion. The practical training cells will be analogous to a university prac. The theoretical training stations will focus on knowledge transfer of core principles of the Fourth Industrial Revolution and their technologies. The practical training stations will involve practical hands-on learning applied to individual technologies. The application cells will look at the application of these technologies to simulated real-world environments. Starting with the theoretical training stations, it involves informal 4-hour knowledge transfer, which will be blended in that it will be both physical and virtual curriculum that will be delivered. We will look at adapting existing courses from industry partners so as to not reinvent the wheel. There will be 4 levels addressed in the theoretical training stations, ranging from operator to artisan to engineer or engineering technician, and then looking at the business side of things. These courses will be developed in a modular fashion to address a wide audience. The practical training stations will facilitate 4-hour skills development through practical training. We will have 10 modular stations which will independently address each of the technologies. There will be a customized instruction set using Twilio and WhatsApp, and it will be analogous to university pracs. And again, we will have 4 levels that will be addressed in terms of the training. Here's an example of one of the setups we have, which uses augmented reality to train a person on assembly of a brake system. The interface to the practical stations will be WhatsApp based. This is to enable an easier integration into the system due to students being familiar with the platform. Furthermore, we would be able to customize the platform to generate an instruction set in the language preference of the student. The next component of the Learning Lab are the application cells, and these will simulate idealized work environments and they will involve the application of multiple 4IR technologies on one platform. These applications will be relevant to our cluster and industry partner needs, and there will be very little instructions or guidance comparatively to the practical stations and the theoretical stations. Again, we will be addressing 4 levels of use. An example of one of the application cells involves the assembly of a digital locker used to dispense medication to chronic patients. Here you see pictures of a system that was assembled and designed locally and used students to perform the assembly process. An example of the application cells includes the development of digital lockers to dispense medication to chronic patients. These machines were developed locally and assembled by students, and they use the following 4IR technologies, including simulation, big data, robotics, industrial Internet of Things, cloud and edge computing, as well as system integration. Here we see the final product of what was assembled in the process. We will be using this as a use case for an application cell in the Learning Factory. Moving on, the research labs consist of the Innovation Center as well as a digital platform. The digital platform will be used as a database for capturing and housing information on state-of-the-art 4IR tools. The Innovation Center will be used for innovation and de-risking of 4IR technologies in the form of R&D, testing, simulation, and feasibility studies. It will also support maintenance, repair, innovation, and localization of products for the Learning Lab, experience centers, and industry. This is some of the work that's going on in the research lab. The last component of the Learning Factory are the experience centers, and currently we have 3 components to them: ventilator production, the AeroSwift 3D printer, and digital transformation of chemical production systems. Fundamentally, the experience centers will give students a chance to experience how 4IR technologies can make a difference to a business. They will support experiential learning and innovation and provide de-risking of technologies and industry applications by serving as a testbed. These are actual working environments. One of the projects that we have on the go deals with the production of ventilators for the National Ventilator Project. Using the 4IR technologies, we will streamline the process of further production of BiPAP ventilators at the CSIR. Here you see a picture of the AeroSwift 3D printer. The Learning Factory will house the technologies to instrument this facility such that we can gain insight into its operation and possibly provide an opportunity for business improvement. The technologies that will be used include simulation, big data, robotics, industrial Internet of Things, cloud and edge computing, additive manufacturing, and system integration. As we mentioned before, the Learning Factory at the CSIR would serve as a reference for the learning factories that will be developed at TVETs around the country. The function of the learning factories at the TVETs will serve local industry needs, local government needs, local academia needs, as well as support centers of specialization. In conclusion, digital transformation will have to inarguably occur across every sector and business eventually to ensure their sustainability. The key technologies that enable digital transformation will be housed in the Learning Factory. We've also discussed the key technologies that enable digital transformation. We've also touched on skills development being crucial in the adoption of these technologies to create change. Innovation and research is crucial to application of these technologies as well across identified key sectors. The Learning Factory is suitably poised to serve as a skills development platform and innovation platform for training and research. We will be developing a Learning Factory by 2022, and a demonstrator of the Learning Factory will be developed by February 2021. This will be heavily reliant on the input from industry partners. There are certain use cases that exist within the CSR, and the Learning Factory will build on these. This is application to healthcare, mining, manufacturing, agriculture, energy efficiency, as well as logistics. Thank you, and we are open for questions now.